Hello guys, we'll be doing this past paper. This is AS level chemistry paper 2-1 of October November 2021. Okay, so the first question says that sulfides are compounds that contain sulfur but not oxygen. Okay, carbon disulfide CH2 is a volatile liquid at room temperature and pressure. State the meaning of volatile. Okay, so this is very basic definition. Volatile means a substance is called as volatile if it is easily evaporated. But just write a substance that is easily evaporated. You can just write easily evaporated and you will get the mark. Easily evaporated. That's it. Okay, so next part. Then it says draw a dot and cross diagram of CS2 molecule. Okay, so how are we going to do that? In CS2 molecule, what happens is there's a carbon atom. It's bonded to two sulfurs with a double bond. Okay, so you're just going to draw the dot and cross diagram. It will be like these circles, which you call outer shells, valence shell. Okay, so this is the carbon atom and this is the sulfur atom. This is the sulfur atom. Obviously the diagram is not that clean, but I'm just drawing a rough diagram and you can do it yourself. And so between each carbon and sulfur there's a double bond, right? There's a double bond here. Double bond means 4 electrons, 2 shared by carbon and 2 shared by sulfur. So now sulfur is from group what? Let me look at the periodic table. Group 16. So which means that it has 6 electrons in its outer shell, in which 2 are used in bonding with the carbon atom. So still it has 2 lone pairs. If you forget to draw the lone pairs, you lose a mark. So you got to draw them. There was another way to draw this, and that was, look, the carbon atom is here, and then a cross and a dot and a cross and a dot. Sulfur, let me just draw it a bigger version. Okay, the same thing here, dot cross dot. It's the exact same thing. There's no difference in that, but you got to draw the lone pairs like that. Okay, same thing here. You can do it both the ways, they both are fine. Now what is the bond angle in CH2? Look, it's a linear molecule. We look at the central atom. Central atom has the central atom. Carbon has no lone pairs. It has no lone pairs. So it is what? It is an AB2 type molecule, a linear molecule. So the bond angle will be what? It will be 180 degrees. Next part. CS2 is a liquid under room temperature. Okay, liquid under room temperature. What is CO2 is a gas. What causes the difference between the physical properties? Okay, this is a very simple question. Here's a carbon and here's a carbon. Okay, the 2 oxygens here and 2 sulfur here. So we know that sulfur has more electrons than oxygen. So just write that down. That quickly, just let's complete this question. That CS2 has greater number of electrons. So it has stronger van der Waals forces. It has stronger van der Waals forces than CO2. Look, when the number of electrons increase, it means what? It means that the strength of van der Waals forces also increases. You gotta remember this rule, that strength of van der Waals forces also increases. So you just gotta remember this rule. Okay, now this question, next part, B part. The enthalpy chain of combustion. Remember, it's combustion. Okay, combustion is represented by the following equation. Okay, define the enthalpy chain of combustion. This is very simple. So what you gotta write is, it is the enthalpy change that occurs when 1 mole of a compound, not a compound actually, you're going to write a substance because it can be an element too. A substance is completely burnt in oxygen. That's your statement, and you will get 2 marks for that. Okay. The table shows enthalpy changes of formations. Remember it's formation now, of CH2, CO2, and SO2. Use the data to calculate the enthalpy change of combustion. Okay, so look, we know this equation, right? Enthalpy change of formation for any diatomic molecule is 0. So this is 0. Formation, okay, this is 0. This is given, this is given, this is given, and this is delta H for this reaction, which is combustion because it is combusting. This is CH2 is burning. So what you're going to do is basically this guy is this standard enthalpy change of combustion is basically the enthalpy change of reaction. Okay, so what you're going to do is you're going to apply a formula, and that formula says that the total, or we're going to calculate enthalpy change of reaction, which is in this case combustion, is equal to the sum of enthalpy changes of formation of products minus reactants. You got to remember this formula. This is a very commonly used formula. Minus the sum of enthalpy change of formation of what? Of reactants. So you're going to put in the values, and do remember about the moles if there are any. So what we're going to do is products are what? These two are products, right? So now there are 2 moles of SO2. Do remember that there are 2 moles, 2 times this, or 1 times this. So you can just put that in. That is minus 394 plus 2 into minus 297 by 2, because there are 2 moles of SO2 minus of reactants. O2 is 0, as I told you. CS2 is this. That is plus 89.7. So you're just going to calculate this, and your answer will come out to be what? Your answer will come out to be minus 1080, okay, to the nearest 10 kilojoule per mole. No need to write the units even. Units are given for you, so our answer is 1080. Next part. Hydrogen disulfide. Hydrogen sulfide is slightly soluble in water. It acts as a weak acid in aqueous solution. What is meant by the term weak acid? Okay, so basically a weak acid is a substance or type of acid that partially ionizes in solution. So just going to write partially ionizes when in solution. That's it. You'll get the mark when in solution. Okay, next part says give the formula of conjugate base of H2S. Okay, so this is very simple. When this is added to water, H3O forms, so one hydrogen is taken from H2S. So what we're left with is conjugate bases are negative. Why? Because they bases are negative. Okay, negatively charged. Okay, so you're right. What is HS minus? Look, so what happens is actually H2S reacted with water, forming H3O positive. Always this forms. Okay, so whenever there's an acid, H2S is an acid, it's saying it acts as a weak acid. So plus 1 hydrogen went from here to there, so 1 hydrogen would be lacking in, sorry, from here to here, so 1 hydrogen would be lacking in HS, so that would be HS negative. So this was the acid here, and this is the conjugate base of that acid. So just go to write conjugate base of that, so it is HS minus by this explanation. Okay, so next part. H2S reacts slowly with oxygen dissolved in water. Okay, this is the equation given. This reaction is represented by the following equation. This is the equation with reference to oxidation number, while this is a redox reaction. Okay, This is pretty simple. So we're just going to write that sulfur here is, what is sulfur here? Sulfur here is -2 and sulfur here is 0. While what is this changing? Oxygen is 0 here and oxygen is -2 here. Okay, so two things are happening. Do note that one is this and one is this. So it's going to write oxidation state of sulfur increases from, you got to put the values in -2 to 0, which means that it is what? It is oxidized. Next part, oxidation number of, similarly oxygen decreases, so it is reduced. So it's a redox reaction. That, as simple as that. You got to put the values in for the oxidation states because it says with reference to oxidation numbers. Okay, oxidation state of oxygen decreases and decreases from 0 to -2, which means that it is reduced. If you're wondering from where did the 0 come up, remember that any element on its own or a compound on its own not having a charge, its oxidation state is 0. For example, this whole compound was equal to 0, but hydrogen is +1. It's two of them. So like, look, 2 hydrogens plus sulfur will be equal to 0. So hydrogens are +1, so plus sulfur, this will be equal to 0. Sulfur will come out to be minus. So that's how you calculate the oxidation states. Next part. Okay, so the compound As2S3, which is, I don't know the name even, maybe astatine sulfide or something, is heated strongly in the air as it forms a mixture of the products. This guy is heated in the air in the presence of oxygen, combustion basically. A sample of this mass of this is placed in 0.1 dm cube of pure oxygen and excess in the reaction chamber connected to the gas range at room temperature. Okay, the reactants are heated until no further reaction is observed. Okay, the products are then allowed to cool to the room temperature. Okay, calculate the volume in dm cube of the gas present at the end of the reaction. Calculate in dm cube the volume of the gas present at the end of the reaction. Okay, molar volume is 24 mole per dm cube under these standard conditions. Okay, molar volume, we know that molar volume is that. Okay, now next part is assume that the pressure is constant, show your working. How many marks is this? 4. Okay, so now how are you going to work it out? Look, so first of all, what you're going to do is, we're given the mass of that As2S3, right? We'll find the moles for that. So we're going to find the moles for As2S3. So moles is equal to mass over mR. Mass is given 0.198 and you can find the mR from the periodic table. Okay, periodic table, so it will come out to be, it's 2 into astatine is 74.9 plus 3 sulfurs, that is 32.1. So you're going to find the moles from here. You'll find the moles as 8.05 times 10 to the power minus 4 mole. You get 1 mark for this working. Okay, next part. Now what you're going to do is the ratio of As2S3 to the ratio of SO2. What is the ratio? 2:6. 2:6. So 1:3. So if this is 8.05 times 10 to the power minus 4 x, so it's got to cross multiply these together. So you'll calculate your x as what? 3 times 8.05, and that actually comes out to be 2.41 times 10 to the power minus 3 mole of what? Of, no, I did this way too bigger. Okay, so you gotta learn that, of SO2. Now look, the question is saying calculate the volume and dm cube of the gases present at the end of the reaction. So SO2 is a gas obviously it will be made during the reaction, so it will be present inside the gas syringe, while some of the oxygen might be left. I'm not saying it should be left, it might be left, we don't know, we're going to calculate that. So if it is left, it counts as a gas because it is a gas. Okay, so let's see if it is left or no. If it's not left, then this is our answer, the volume of this. But if it is oxygen is left, then we're going to add the oxygen volume into the volume of SO2 at the end of the reaction. So that will be our volume in the gas syringe at the end of the reaction. So now what we're going to do is find the volume of SO2. It's very simple. Volume is common. Volume is equal to moles into 24 molar volume. Okay, so we're going to do what is multiply this value by 24. Okay, so you're going to do what is 2.41 times 10 to the power minus 3 into 24, and you'll get your answer in dm cube. That comes out to be 0.0579 dm cube. Now you're going to do what is apply the ratio as2 as3 to the ratio of what? The ratio of oxygen. That ratio is 2:9. How do I know that? 2:9. Okay, so 2:9. Now apply the same molar volume. So if it is 8.05 times 10 to the power minus 4, there will be x. It's got to cross multiply, and your x will come out to be what? Your x will come out to be 3.62 times 10 to the power minus 3 mole. Okay, now this is the wall. This is the this much moles of oxygen reacted. Okay, so what I find the volume of oxygen reacted, again same formula, volume is equal to mole into 24 dm cube molar volume. So put the value in for oxygen, 3.62 times 10 to the power minus 3 into 24. This is the volume of the oxygen reacted. Your answer will come out to be 0.0869 dm cube. This is your answer for volume oxygen reacted. So how much is oxygen remaining? This was the volume of oxygen, guys. Do you remember that? So how much is left? How much oxygen is left? Left oxygen. Left. This was a tricky question. Left amount of oxygen is what? 0.1 minus 0.0869. This is the volume of oxygen reacted. This is the total. So what is left? Left is 0.0131 dm cube. What is the total volume of the gas is present at the end of the reaction? This much oxygen left over, and this much, where is it? This much SO2 produced. So what is this? This is SO2 produced, volume of SO2 produced. You can add these two values together. So total volume will be the sum of this and sum of this. So you could add a total volume of gases at the end of the reaction, and your answer will come out to be 0.071 dm cube. What I've done here is actually you would add this volume of SO2 produced into this volume of oxygen remaining. Next part, state environmental consequence of SO2. Obviously it will lead to acid rain. Just go to write acid rain, and how it will get further oxidized to form SO3. SO3 will react to water vapors to form acid rain. SO2 can be removed with reacting it with NaOH. Construct an equation with SO2, and okay, so SO2 is what? It is acidic. So acidic oxides of period 3 will react with bases. So this is very simple question. So you could write what is NaOH plus SO2. What will it form? It will form Na2SO3. Okay, so and plus H2. You got to remember these. If you look at the periodicity property chapter, there are reactions of acid-base behavior of period 3 oxides, so it is included in that. Okay, then you got to balance that. 2 sodium on the right hand side, there must be 2 here. I think so. This should be balanced. Now what we left is include state symbols. So we write state symbols. NaOH is aqueous. This is gas. This is aqueous. okay, because it is soluble, that's why it's aqueous. So what is the name of this compound? It is sodium sulfide, not sulfate, sulfide, IDE. Okay, we've done this. So this was worth 21 mark question. Okay, so we've done that question. Next part. Now, some of the reactions of calcium are shown. Okay, calcium is what? Calcium is a group 2 element. We know that, okay? Reaction 1 produces calcium nitrate and one other product. Identify the other product. No, reaction 1. There's the reaction. Okay, so whenever we're adding HNO3 is what? It is nitric acid and it is an acid. Whenever acid react with a metal on its own, we get a salt and hydrogen gas is produced. Just got to write H2 or hydrogen. It's your choice. Hydrogen gas. That's it. Construct an equation for thermal decomposition of calcium nitrate. Whenever group 2 nitrates decompose, they form what? They form group 2 oxide, nitrogen dioxide and oxygen. But you have to balance these equations. How are you going to balance is there are six of the oxygens on your right, and how many are here? Sorry, the 6 oxygens on the left, and 1 2 3 4 5 are here. So what you're gonna do is that you're gonna balance these equations. And how are you gonna balance these equations? There is 1 and 2 is 3 and 2 is 5, and there are 6 oxygens. So first of all, do what is balance it. Put 2 here. When I put 2 there, I'm gonna put 2 here. Okay, and obviously 2 here. Now how many oxygens are there? 6 into 2 is 12. Here are 2. Here are 4. 2 and 4 is 6. We need to make it 12, so we're gonna put 3 here. So that is your equation balanced. Next part. Trend in thermal stability of group down nitrates, it increases down the group. You don't need to write down the group because it is already said down the group. Increases. In reaction 3, CO2 is bubbled through water containing calcium carbonate. A solution of CaHCO3 twice forms. We don't know what is that, and you don't need to remember that even. Just go to write the equation. That's it. That CO2. Now let's start with the calcium carbonate. Calcium carbonate plus water plus CO2 forms what? CaHCO3 twice. Okay, reaction 3. He's already told us that, look, when CO2 is bubbled through water, it contains this compound, and this compound 1 plus 2 water, and this is third compound. It will form a solution of this compound. If you want to put this in reaction 3, where's the reaction 3? Look, in this particular reaction, calcium carbonate plus water plus excess CO2 will make this compound. We don't know what is that compound. Just write the equation, that's it. And you gotta write the state symbol. This is solid, this is liquid, this is gas, and this guy is aqueous. How do we know that? It's given here. How CaOH2 is used in the agriculture. You can write many things. Maintains pH of soil, maintains pH of soil. You can write increases pH of soil, it reduces acidity of the soil. There are many answers. Whatever you find correct, you can write it. Now in reaction 4, calcium carbide CaCO2 is formed from CaO. Let's have a look. Reaction 4. This was calcium oxide. When carbon is added, it forms calcium carbide, or whatever the name is. So CaCO2 contains C2 minus anion. We don't know what is that anion. Maybe carbide. Yeah, it is carbide anion. So, and a carbon is, each carbon in C2 minus 2 is sp hybridized. How sp hybridized orbitals are formed? This is very simple. sp orbitals are formed when an s of an atom overlaps with 1p of the other atom. Okay, sp overlap he's asking us, so you're write 1 s and 1 p orbital overlap. Okay, so this is how sp orbitals form. Now he's saying sketch a diagram to show how two sp hybrid orbitals can form a sigma bond. Now we know that what is a sigma bond. Sigma bond is a single bond. Okay, so just have a thinking. Look, this is an s orbital. Okay, so and this is the sp. Then I'm gonna have another one. I'm gonna have another one like maybe somewhere here. Okay, so this is another, this is one sp and this is one sp. We're overlapping them because we're forming hybrid orbitals. So now what's gonna happen is the overlap will give you some sort of shape like that. Okay, you don't have to show any of these. I'll tell you the final answer. I'm just trying to explain it. Okay, so now one here. Okay, so this is the overlap. This is the overlap. I've shown it here. I can't show it very nicely, but it's fine. You don't have to show this. You don't have to show this. It is. I'm just explaining it. Now, what your final answer should like that is like, look, way too big. Okay. Okay. Now another of the same size s orbital. Now something like overlap like here and here. You gotta put an electron here and an electron here to show that this is a sigma bond. Sigma bond is a single bond, and all single bonds have one pair of shared electrons. You gotta remember this, okay? That is your final answer for this question. Just remember that. How do we show this? Just remember this shape and don't forget to show these. Okay, so I've shown you how do they form, and you gotta remember that this is how sp looks like. Just don't think about anything else. That's it. Remember that as it is. Next part. The flowchart shows some of the reaction of calcium carbide. Reaction 5 can be used to prepare NH3. Okay, to produce what? To produce ammonia. Okay. Calculate the minimum mass in tons of calcium cyanamide. Okay, that is required to produce this much amount of tons of ammonia. Although he's given us is the main thing, and this is the main thing, and you can easily work it out. This much we need to produce this much mass of ammonia. So first of all, find the moles of ammonia, because we're relating everything in molar volume, molar ratios. We're talking about reaction 5. Okay, so moles of ammonia will be N is equal to mass over mR. Mass is what? What is the mass? 1.5 times 10 to the power 6 times 10 to the power 6. We're going to make it in grams because mR is always in gram. mR is 17 of ammonia, okay? For NH3, right? We're talking about NH3. Okay, so what is the moles? It is 8.82 times 10 to the power 10 mole. Now you got to apply the molar ratios. Okay, so this is ammonia. This is reaction 5 given. It's 2 ratio, how much of CaC into is needed? 2 ratio 1. So it's 2 ratio 1. So look, CaC and 2 to the ratio of NH3 is 1 ratio 2. So if this is 8.82 times 10 to the power 10, this will be x. So just multiply this value of NH3 by 2. So x would be what? 8.82 times 10 to the power 12 multiplied by 2. Your answer will come out to be what? What would be your answer? Don't have to multiply, you have to divide. Sorry, my bad. Your answer will come out to be 4.41 times 10 to the power 10 mole. He's asking us mass in tons. If you are wondering why did I divide, look like that, multiply. Okay. Okay, so we have found the moles of CaCN2 required. We're gonna find a mass. Mass is equal to moles into mR. Moles is known, 4.41 times 10 to the power 10. mR can be calculated from periodic table, and that would that would come out to be what? It is 80.1. 80.1. Your mass will be what? But you gotta do what is multiply this by 10 to the power 6. Why? Because we want the answer in tons. Okay, not multiply, you have to divide this time. I'm actually sorry. I'll tell you why do we have to divide. Okay, so your mass will come out to be what? It will come out to be 3.53 times 10 to the power 6 tons. 3.53 times 10 to the power 6 tons. Okay, so look, here we have to convert this much tons into grams. You're going to multiply by 6. Now here we have grams, not this. Where is the grams? So our answer here, we're dealing here everything in grams. Everything we have calculated by using grams. So we're gonna convert grams into tons, because the answer he wants in the tons. You gotta divide by 10 to the power 6. You gotta divide, okay? So when ton into gram, we multiply by 10 to the power 6. And gram into ton, we divide by 10 to the power 6. Yeah, I hope you get it. Next part. Draw the structure of organic products formed in the following reaction. Okay. So first reaction is this is a halogen alkane. When we add NaCN, nucleophilic substitution reaction occurs, right? Nucleophilic substitution reaction occurs, and Br is substituted, replaced by a CN. So it will be CH3, CH2, CN. That's it. NaBr is a byproduct, but we're not supposed to write it because they're asking us the organic product only. Next part. Now when we acidic hydrolyze it by adding an acid, CN is replaced by Co. Everything remains the same, the rest of it. CH2COH. That's it. Now this is a ketone. This is an alkyl group. This is an alkyl group. So when we add NaCN and HCN in it, what happens is everything remains as it is. There is a CN added here, and O is there and H is there. Hydroxynitrile. This is called as hydroxynitrile. Okay, not the name of this classification of the compound is hydroxynitrile. This reaction is called as nucleophilic addition. This is nucleophilic substitution, and this is acidic hydrolysis. You don't need to write the name, just telling it. Okay, this is correct, this is correct, and this is correct. That's how you gotta do this. You gotta draw those. This was out of 13. Next question. Phosphorus is the reactive element of period 3. Okay, it has several allotropes. What are allotropes? Allotropes are the form of same element. Allotropes are different forms of the same element. Like carbon has allotropes, diamond and graphite. Similarly, phosphorus also has allotropes. Details of two allotropes are given. This is white phosphorus, red phosphorus. White phosphorus formula is this, melting point is this. Red phosphorus is P, and P has melting point of 590, very high. White phosphorus and red phosphorus have the same covalent bonding, suggest a type of structure shown by white phosphorus and the red phosphorus. So explain why red phosphorus P has a greater melting point than phosphorus, white phosphorus. Is very easy. Structure of P4, what does it tell from your melting point analysis? What is the structure of P4? Obviously it is simple molecular. You don't need to remember anything in it. Low melting point, they both have covalent bonding. You gotta write simple molecular. High melting point, they have covalent bonding. Means what? Giant molecular. Giant molecular structure. Wow, why do I know that? You don't have to write. I'm just saying, how did it reduce because of low melting point? How did it reduce high giant molecular? High melting point. And remember, they both have covalent bonding. It's given in the question. Now, what's the explanation for this? Explanation must be very simple. The melting point of P4 is low because it has weak. We're just suggesting, right? We might be wrong, might be right. We're just suggesting from this data given. P4 has weak van der Waals, while P has strong covalent bonding. Okay, just gonna write that weak van der Waals forces. So this is a simple molecular structure, weak van der Waals forces. Okay, while P has a strong covalent bonding. Because of that, stronger van der Waals forces. That's why this deductions. Okay, next part. Red phosphorus peak forms P4 when exposed to sunlight. This is the delta H. Before reading the question, delta H, this means exothermic reaction, right? Energy is released to the surrounding, energy is lost to the surrounding. Draw reaction pathway for the reaction of conversion of phosphorus P to red phosphorus. Exothermic reaction. Products have less energy in the reactant. You're gonna do it as something like this. And here will be what? Here will be P. You label the graph. Activation energy always positive from the reactants to the hump of the graph. EA. This is delta H, negative. Okay, this is delta H, which is always negative. Okay, so you will get your 1 mark here. So only 1 mark. Some of the reactions of P4 solid, which was what? Red phosphorus, I think, or white. It was white phosphorus, are shown in the reaction scheme. What is the oxidation number of phosphorus in this? Okay, I told you every compound is 0. So there are 4 phosphorus and 10 oxygens. This is an oxygen, right? 10 oxygens is equal to 0. Every compound on its own is 0. Every compound on its own, I'm just repeating it again, it's very important, it is 0. Okay, so we don't know phosphorus, right? Oxygen, we all know it's -2. The oxidation state, you got to remember that, is equal to 0. So from here, 4p will be plus 20 when this goes there. And so 1p will be plus 20 over 4, which comes out to be plus 5. So you got to write plus 5 here. That's it. Nothing else. There's no hard rule in it. Okay, next part is what? Reaction 1. It says PCl5 when reacted, reaction 1. PCl5 when reacted with water forms Q. So what is Q? We need to, this is hydrolysis reaction. We need to remember that phosphoric acid forms and HCl forms. Phosphoric acid plus HCl. We've got to balance this equation. How many chlorines are there? 5 should be here because there are 5 chlorines here. Okay, 5 on the right hand side now. How many hydrogens are there? 8 hydrogens, so there must be 4 here because this is times 2. That equation is balanced. If it is P4 or 10 plus hydrogen, we just get this acid, phosphoric acid. No HCl this time because there is no chlorine here. And we're going to balance this equation. 4 phosphorus means 4 here. 4 here means 4 here, right? So how many hydrogens are there? There are now 12 hydrogens. So you gotta add 6 here. 6 into 2 is 12. Now oxygens should be balanced there by their own. Triphenylphosphine is, you gotta be very scared by just looking at a structure, right? So this is a type of reaction known as Witting reaction. It is used in the reaction known as Witting reaction. Even I don't know what is Witting reaction. So triphenylphosphine is given. What's the empirical formula? This one structure is C6H5. So how many are there? There are 3 of those. So C6 into 3 is 18. 3 into 5 hydrogen is 15. So there are 3 of, so we get this formula, and there's 1 phosphorus P. This cannot be further simplified, so this is hence the empirical formula. Empirical formula is the simplest formula, simplified molecular formula. This is a simplified molecular formula. This is very easy question, full marks. Okay, so next part. In Witting's reaction, an aldehyde reacts with a halogen alkene to form an alkene. Guys, this is not testing anything from the syllabus, but it is in the syllabus. Why? Because it's testing your skills. Let's see. Everything should be given in the question, right? You just got to use your brain, your mighty brain, to just think of the answer. The conversion is shown in the following reaction. This is Witting's reaction. Okay? Just forget about it for now. Compound H can be made from propanol. Stage 3 in the reaction scheme is a wetting reaction. Okay, compound H, this is compound H, can be made from propanol. First stage, second stage, three stages. So conversion of propanol into the stage compound H is a three-stage process. So what is the type of reaction? Reaction 1. This is what? This is a reducing agent. So what type of reaction is actually occurring in what? In stage 1, it is a reduction reaction. Reduction. The reduction of aldehydes produces what? Primary alcohol. Some primary alcohol. Primary OH. Primary OH, when reacted with rich phosphorus and iodine, this is a substitution reaction for alcohols. Substitution reaction. OH is replaced by iodine. Daughter structures of G and H. Now what will be G? G is a 3-carbon, there's a 3-carbon alcohol on the rightmost carbon atom. So let's do it. CH3, CH2 and CH2OH. What is the name of it? You don't need to write. Propan 1. Oh, you have to draw the structures. Remember that. Just naming it, okay? So I told you have to remember what is aldehydes when reduced. Produce primary alcohols. Primary alcohols, from this one, it has 3 carbon atoms, so it will be some propanol. We don't know propan 1 or propan 2, but it should be propan 1-ol. Why? Because the structure of this was the double bond with oxygen was on the rightmost carbon atom like this. When reduced, hydrogen is added, this goes away and one more hydrogen is added. So yeah, so this is propan 1-ol. So you got to remember that. H is here. This added plus a halogen alkane and an aldehyde. So this H must be some alkene. You must be wondering, how do I know that? It's given. Wetting reaction and aldehyde react with the halogen alkane to form an alkene. Now look, this is what? This is a halogen alkane. No, this is an aldehyde. This is a halogen alkane, and we get an alkene here. How do we know? Carbon-carbon double bond here. Carbon-carbon double bond there. Okay. So what is our R1 and R2? R1 and R2. C2H5. Look, this is a carbon atom here, and then the rest of it is R1. Right? How many carbon atoms are there? There are 3 carbon atoms. 2 here, 1 here. We're talking about aldehyde. 2 here and 1 here, right? So there are 3 carbon atoms, out of which 1 is here and 2 must be in R1. So what is R1? This part is R1. This part is R1. Same for the halogen alkane. There is carbon here. How many carbons left? 2 carbon atom in the R2 chain. So this is again R2. So this R1 is this R1. Well, this guy for the halogen alkane, which is R2, is here. Well, R1 and R2 are basically the exact same thing according to this question. So now I'm just going to draw the formula. That's it. Just remove the CHO and CHI2 because of wetting reaction. Just going to draw the formula. Let me just do it. It will be something like this. Look, C2H5. This is our C2H5, which is bonded to a carbon atom here. Right, which is bonded to a hydrogen, and then downwards it is double bonded to a C, which is bonded to an H, this H, and an R2. R2 is C2H5. So you got to draw the formula. Just got to write that here. C2H5 bonded to what? C2H5, which is bonded to a carbon, right? Carbon, which is H, and then another carbon, which is CH, double bond here, and another C2H5. You just got to write the structure here. You can also draw exact same thing, doesn't matter. C2H5, CH, double bonded to another CH, which is bonded to C2H5. So that's how you got to do it. This was R2, which is this. This was R1, which is this. While everything is like that, that's how you're going to show according to this. Everything actually is given in the question. I hope this is clear. Next part. Okay. Identify the organic products formed when compound J, this is an alkene. How do I know that? Carbon-carbon double bond is treated with hot concentrated acid flight. So what is happening here? This is an oxidizing agent. So this gets oxidized. So what is going to happen? Look, whenever there's a carbon-carbon double bond and that carbon which is doubly bonded, it has methyl group, you're gonna get a ketone. So how many carbon ketone? 1, 2, 3. 3 carbon ketone. 3 carbon ketone is what? Propanone. You're gonna write propanone. This is a rule. When we oxidize alkene with hot oxidation, not cold, hot oxidation, and doubly bonded carbon in that alkene has a carbon-carbon double bond, there will be a ketone form. Now, how many carbon atoms used here? 3. 1, 2, 3 are used. Doubly bonded carbon has methyl group and double bond. Okay, so doubly bonded. Okay. Now, how many carbon atom? 1, 2, 3. So 3 carbon would be the acid, carboxylic acid, CH3, CH2, COH. That's it. You will get your 2 marks here. I hope this was easy. This is not hard. Actually, got to learn these rules. That what do we form when we treat it with hot cheminophore? Whenever there's a carbon that is doubly bonded and has a methyl group, we get a corresponding, whatever it is, corresponding according to carbon atoms. How many are there? The ketone. And rest, if there's no terminals means CH2 bonded to that on the side. If this is there, then we form carbon dioxide plus H2O for that terminal, and the rest part is basically carboxylic acid or ketone or whatever it is depending on the compound. There's no terminal here. This is CH3, right? So 1 carbon, 2 carbon, 3 carbon. This is 3 carbon. It will be terminated to and carboxylic acid, whatever it is. Now 3 carbon carboxylic acid is what? Propanoic acid. So you gotta remember that. Okay. You gotta learn everything. So next part. Compound B is a liquid with fruity smell. Okay, so what can be compound B? And the main thing is it has told us it has a fruity smell. So by fruity smell, what do we mean? We mean that it is an ester. Okay, and you can also see that there is an ester link there. Look, there's an ester link here. Whatever here, we don't care. This is an ester. That's why it has a fruity smell. The reaction scheme shows how this B, whatever this ester is, can be made from ethanol. So we're using ethanol here. How it can be made from ethanol? Okay. Reaction 1 is an oxidation reaction. Okay. Give reagents and conditions. Reagents are different. Conditions are different. So what are you going to write? Reaction 1. This is what? This is a carboxylic acid. Do you remember that? This is a primary alcohol. So you're gonna do what is you're gonna put acidified potassium magnate, oxidizing agent, a good oxidizing agent, acidified potassium magnate, and heat under reflux. That's it. You'll get 2 marks. You can't write. Don't write distill here. Heat under reflux, because you can't write distill because we distill for aldehyde. If we distill, this might be converted into ethanol. We don't want that. We wanted direct strong oxidation directly into a ethanoic acid. Construct an equation to represent reaction 1. We just did it. Very simple. C2H5 OH. This is 5. Okay, don't mess it up. OH C2H5OH plus oxidation by cheminophore. It will form what? It will form a CH3 and COOH, 2 carbon carboxylic acid, and high water is always produced. So how many oxygens have been added? Actually 2 oxygens. There was one already here, so one is here and one is in the water. 2 hydrogens have been added. Number of what? Number of the hydrogens are already balanced. This is this type of reaction 2. Reaction 2 is a bromine being added here. So it's a substitution reaction. Some hydrogen in this carbon atom might be getting substituted by bromine. So just write substitution. You don't need to write anything else. Not the specific type of substitution. It is just substitution. We don't know. Okay, so H2SO4 acts as homogeneous catalyst in reaction 3, homogeneous catalyst ester production. There was ethanoic acid, sorry, not ethanoic acid, one carbon, two atom. So there's some acid, some carboxylic acid with bromine attached, whatever the name is. We added ethanol into it, and H2SO4 is acting as a catalyst. Why does this describe it homogeneous? Same physical state as the reactants, or you can write same phase at the reactants. This is what homogeneous. Heterogeneous means different physical state or different phase from the reactant. That's it. Now the next part. How much of it is actually left? This is, I think, the last question. Yeah, it is. Okay, reaction 2 needs to take place. Reaction 2 needs to take place in the absence of water to prevent the formation of C. Where's reaction 2? This guy needs to take precedence in the absence of reaction 3. Okay, so if C is present in the reaction mixture of the reaction 3, a different compound D will also form. Okay, the compound D has two identical function groups. So what he's saying is, if something else is produced here, maybe compound C, instead of this we get C, then in reaction 3 we won't get this, we'll get something else which is D. We don't know what is D. So D has two function groups, identical function groups. Okay, infrared spectrum of D shows strong absorptions at this range and at this range, but no absorption due to OH. Use your data booklet to identify the function group present in D. Nothing very serious. Just got to explain why this range is there and why this range is there in compound D, using your data. So it is an ester. First of all, why? Because there's a CO peak at 1100. Use your data booklet. The data booklet has this every information given that where this peak of this bond is occurring. Okay, so that 720 per centimeter absorbance is of what? That is of carbon-carbon double bond. That is also present in esters, right? Present in esters. Now you can't call it a carboxylic acid. Why? Even though this might be produced in carboxylic acid, this is present in carboxylic, but it's not a carboxylic acid. Why? No absorption due to OH per D. It is not a carboxylic acid. No OH peak. 3 marks. You get your marks here. I'll write all of that. Okay, that's it. So other reactions of C are shown. We don't know what is C, but he's given us the formula. Oh, C was given here too. Okay. Draw the structure of E. Where's E? Here. So this is some carboxylic acid and alcohol in the same thing. So when it is added, so when Na2CO3 is carbonate only reacts with what? It only reacts with the acid group. Carbonates react with acid group. What is the observation we get? He's not asking us, just explaining effervescence. Okay, do remember that. Right, draw the exact same thing, guys. Exact same thing. One down, and here's an OH. This double bond stays as it is, and there's an O here as it is. H is gone, and we get an Na here. This is negatively charged. Okay, negatively charged. This is positively charged. You will get your mark. Okay. Don't do anything to alcohols because we're reacting not with Na, it's Na2CO3. Only reactor is carbonate. Okay. Sorry for the noise. This is some bike, I don't know, some guy going crazy. Okay. Suggest why NaBH4 is not a suitable reagent to make this from C. Explain your answer. Look, NaBH4 is not a strong reducing agent. So it will not be able to reduce this carboxyl group. It is very weak. So what we use is LiAlH4. We use it for carboxylic acid. NaHB, what is that? Yeah, NaBH4 is not used for carboxylic acid. Okay, do remember that. It is a weak reducing agent. Or you can write not strong enough reducing agent. Now this is a substitution reaction, and alcohol is reacting with SOCl2 to form G. Very simple. So it's going to write CH2OH whole twice with SOCl2 forming G, and G is given CH2Cl whole twice. Now what else form? Sulfur dioxide. What else form? H2O. No need to balance it. It should already be balanced. Okay, so you will get your mark here. You got to remember these equations, that in the formation of chloroalkane we have 4 equations. Reaction of alcohol with PCl, PCl5, PCl3, HCl, or SOCl2. You got to remember all these 4 equations. They have all the byproducts, everything you have to remember. Okay, so this is one of those chloroalkane formation from alcohols. You can go and maybe check it from a test book or your notes or whatever. Now, why is C very soluble in water? Why is C very soluble in water? Okay, there's an OH group and OH group, so we can say it forms hydrogen bonding. It can form hydrogen bond with the water, so it is soluble. Anything that is soluble in water can form hydrogen bond with the water. It can form hydrogen bonds. Look, whatever, I'm repeating it again, this is important. This can come in physical chemistry too. When a compound is soluble in water, it means it can form hydrogen bond with the water. Okay, so then it is soluble. If it cannot form hydrogen bond, then it is not soluble. So this is 12-mark question. This whole paper is done and dusted. So this is done here. I think we finish it within an hour. So that's it. I hope you understood. Bye.